In Chapter 5, we want to continue our study of quadratic residues. So we'll introduce the Legendre symbol and talk about our main theorem, the law of quadratic reciprocity. So in this section, we'll introduce the Legendre symbol. It'll just be a symbol that's +1 if a number is a quadratic residue and -1 if it's not. We'll outline the basic properties of the Legendre symbol, evaluate the Legendre symbol using Euler's criterion, and then just discover the law of quadratic reciprocity using examples. In the next section, we'll go through a proof of the law of quadratic reciprocity. So let's recall our definition of what a quadratic residue is. So let A and M be integers with A relatively prime to M. We'll call A a quadratic residue mod M if there exists an x such that x squared is congruent to A mod M. So in other words, A is a perfect square. And if no such x exists, then A is called a quadratic non-residue mod M. Now there's no universal agreement on this condition here. I think in the last section I didn't put the restriction that A is relatively prime to M, but for most purposes we go ahead and do that. So here's the Legendre symbol. Let P be an odd prime, A be an integer with P not dividing A. The Legendre symbol, we use parentheses and then a fraction symbol A over P, is defined to be +1 if A is a square, so if A is a quadratic residue, and -1 if A is a quadratic non-residue. Okay, as an example, let's evaluate the Legendre symbol A over 7. So I want to determine for what values of A is A quadratic residue mod 7. And if I'm going to do a whole bunch of values, let's just calculate the different squares mod 7. So 1 squared, 2 squared is 4. 3 squared is 9, which is 2. And then once you get to this point, they just start repeating. So 4 is the same as -3. So 4 squared would be 2. 5 squared would be 4, and you can check that out. 25 is 4 mod 7. And then 6 squared is the same as -1 squared. Okay, so just enumerate what all the perfect squares are, and then we can write these down. So 1, 7 equals 1. So 1 is a perfect square. 4 is a perfect square. 2 is a perfect square. So 1, 4, and 2 are the quadratic residues where the Legendre symbol is +1, and then the remaining 3 values, 3, 5, and 6 all come out to be -1. Okay, Euler's criterion for being a quadratic residue. So we did this last time. With P be an odd prime, with P not dividing A, then A is a quadratic residue mod P if and only if A to the P minus 1 over 2 power is congruent to 1 mod P. So this was the Euler criterion for quadratic residues. And again, the proof was the group of units mod P is a group of order P minus 1, and the GCD of P minus 1 and 2 is equal to 2. Thus, x squared congruent to A mod P is solvable if and only if A to the P minus 1 over 2 power is congruent to 1 mod P. Okay, so we did this last time. Now we're going to rephrase it using the Legendre symbol. So in particular, from this theorem, we see that the Legendre symbol is 1, that is, A is a quadratic residue, if and only if a to the p minus 1 over 2 is congruent to 1 mod p. So the Legendre symbol and the power a to the p minus 1 over 2 both agree when they are equal to 1. And so that leads to the following theorem. Let p be an odd prime, a an integer with p not dividing a, then the Legendre symbol a over p is congruent to a to the p minus 1 over 2 power mod p. So have we already proven this? Not quite. So we showed that if the left-hand side is plus 1, then the right-hand side is plus 1. And if the right-hand side is plus 1, then the left-hand side is plus 1. So we have to think about what happens if these values are not plus 1. Well, note, for any a with p not dividing a, if you take a to the p minus 1 over 2 power and you square that, that would be a to the p minus 1. And what does a to the p minus 1 equal? Well, by Fermat's little theorem, this is congruent to 1 mod p. And so we have something squared, let's call this x right here, congruent to 1 mod p, which of course is equivalent to saying that x is plus or minus 1. We saw this before. So that says that a to the p minus 1 over 2 power is always plus 1 or negative 1 mod p. And that completes the proof. So then, if a to the p minus 1 over 2 is negative 1 mod p, then a is not a quadratic residue, by the preceding result. Right, it's a quadratic residue if and only if this came out to be plus 1. Then a is not a quadratic residue, and therefore the Legendre symbol, by definition, is negative 1. So when the right-hand side is negative 1, so is the left. When the right-hand side is plus 1, so is the left. And so we've got agreement in both cases. Okay, let's repeat the formula we discovered last time for when negative 1 is a quadratic residue. So this time I'll use the Legendre symbol. So proof we saw last time. We saw that negative 1 is a quadratic residue mod p if and only if p is 1 mod 4. And that was immediately from the Euler criterion. So negative 1 to the p minus 1 over 2 is plus 1 when p is 1 mod 4, and it's negative 1 when p is 3 mod 4. So I'm just reformulating the theorem we did last time using the Legendre symbol. Some elementary properties of the Legendre symbol. The first property tells us that it's a multiplicative function. So if we have the Legendre symbol of a times b over p, this is the same as a over p times b over p. Properties 2 and 3 are absolutely trivial. Property 2 just says that the value of the Legendre symbol just depends on the residue class of a mod p. And it's just saying Whether A is a perfect square or not mod P just depends on the residue class. So there's nothing going on there. And property 3 is absolutely trivial. If you start with the square of an integer, and you ask, is the square of an integer a perfect square mod P? Well, yes, of course, because it's congruent to A squared mod P. So that's a trivial statement. So the only thing interesting is part 1. And we'll just use the Euler criterion. So AB over P is congruent to AB to the P minus 1 over 2 power, which is congruent to A to the P minus 1 over 2 times B to the P minus 1 over 2. And this is all mod P. And again, by the Euler criterion, A to the P minus 1 over 2 is the Legendre symbol. And this is the Legendre symbol for B over P. And there you have it. So AB over P is congruent to A over P times B over P. Now, I haven't quite proven part 1 because part 1 is an equality of integers. This is a congruence right here. So how do we go from the congruence to saying these two integers are actually equal? Well, that follows from the fact that since the integer value of AB over P is plus or minus 1, and so is the right-hand side, since the values on the left and right sides are plus or minus 1, how is it possible to have a plus 1 congruent to a negative 1 mod P? That's the question. Well, you can't have it. It follows that AB over P equals A over P times B over P. Right, so what I was just saying is that if you had 1 congruent to negative 1 mod P, that would mean that P should be a divisor of 2, which would mean that P equals 2. But we're dealing with an odd prime in this theorem, so this cannot happen. This cannot happen, so the only way we can have the congruence is if this integer equals 1 when that integer equals 1. Okay, now let's explore the reciprocity behavior. So I'm going to start with the following example. Let's compare P over 3 with 3 over P. So this symbol here, we're asking, is P a perfect square mod 3? Whereas the second symbol, we're asking, is 3 a perfect square mod P? So calculating P over 3 is a very easy task. We just look at the residue class of P mod 3. So what are the perfect squares mod 3? You've got 1 squared, which is 1. 2 squared is 1. So the only perfect square mod 3, you would have to have P congruent to 1 mod 3. So in this table, let's look at the first row. I pick out the primes that are congruent to 1 mod 3. So 7, 13, 19, 31, 37, and 43. And those values are all plus 1. And then for the remaining values, they have to be negative 1. So it's very quick to fill out the values of P over 3. To calculate 3 over P, we just use Euler's criterion and just use a calculator to do that. So for instance, 3, 5 is 3 a perfect square mod 5. you go 3 to the p minus 1 over 2, so that'd be 3 squared, which is equal to 9, which is negative 1 mod 5. And so 3 over 5 is negative 1. And you can do that with a calculator or some computer. And now compare these two rows, p over 3 and 3 over p. What pattern do you observe? So you can pause here if you want to try to discover it on your own. So what we observe is that you get the same value here. Let's try to find where do we get the same value. Okay, and there. So for what primes p are the two values in agreement? When p is 5, 13, 29, 37, and 41. And you'll note that those primes are all congruent to 1 mod 4. And so we note that if p is 1 mod 4, then the two values are equal. While if p is congruent to 3 mod 4, they have opposite signs. And that pattern continues if you kept going further in this table. Next, let's do the same thing for p over 5 and 5 over p for various primes. So this time p is a perfect square mod 5 if p is congruent to plus or minus 1 mod 4, 1 squared or 2 squared. So I go through the primes that are plus or minus 1 mod 4, like 11, 19, 29, 31, 41, and put plus 1s right there. Oops, there's a typo. Those should both be negative 1s. And then for 5 over p, I just calculate it using Euler's criterion, for instance. And this time, what am I observing? Well, it looks like for every prime, we are getting exactly the same value coming out. And that happens all the way down the line. So something is going on here. Is that just a coincidence that things like this are happening? So we see that the values are identical in this case. Well, you can go on exploring further examples of this type. And people like Euler, Legendre, and Gauss did this. And you start finding that this pattern continues. So we observe that whenever we start with a prime that's of the form 3 mod 4, such as q equals 3 in the first example, that p over q equals q over p only if p is congruent to 1 mod 4. And whenever we start with a prime that's congruent to 1 mod 4, such as q equals 5 in the second example, we get agreement for all values of p. So the only time that p over q would disagree with q over p is if we started with q being of the form 3 mod 4 and p was also of the form 3 mod 4. And this leads us directly to the law of quadratic reciprocity. So it goes like this. For any odd primes p and q, p over q equals q over p unless both primes are congruent to 3 mod 4, in which case they have opposite signs. There's an equivalent way of stating it, so you can just write it as one equation, but in practice it's much better to think of it verbally like this. P over q is q over p times this power of negative 1. Negative 1 to the p minus 1 over 2 times q minus 1 over 2. So the theorem was first conjectured by Euler and Legendre and first proved by Gauss. Gauss, in fact, published 6 different proofs, and over the next 2 centuries, literally, not hundreds, but there's probably 100 to 200 different proofs of quadratic reciprocity. And they are all a bit mysterious. This is a genuinely deep result, the law of quadratic reciprocity. So we'll go through a proof in the next section using one of Gauss's proofs and making use of something we call Gauss's lemma. But for now, let me just point out what this factor here is all about. So note p minus 1 over 2. So we just need to know, is this an even or odd number up in the top? So we've seen that this is even if and only if p is congruent to 1 mod 4. So the only way this exponent could come out to be an odd value is if both p minus 1 over 2 and q minus 1 over 2 are odd numbers. And the only way both of them can be odd numbers is if both primes are congruent to 3 mod 4. So that's just a cute little trick for summarizing the two different cases that we're looking at here.